Okay, so we're going to be talking about using confidence intervals wisely. So what conditions need to be met to calculate a confidence interval? Well, random. This has to be random. The data come from a well-designed random sample or randomized experiment. If you don't correctly use randomization, our estimates might be biased, and we shouldn't have any confidence that the intervals we calculate contain the value of the parameter we are trying to estimate. Normal. The sampling distribution of the statistic has to be approximately normal. If this condition is not met, the actual capture rate of our intervals will be often less than the stated capture rate. And independent. Individual observations have to be independent. When sampling without replacement, the sample size N should be more than 10% of the population N. The 10% condition, if you recall. To use our formula for the standard deviation of the statistic. If this condition is violated because we are sampling without replacement, then the actual capture rate will be larger than the stated capture rate. So remember, random, normal, and independent. We've seen these before, so we're still looking for those. What are the three conditions for constructing a confidence interval for a proportion? Well, it doesn't surprise you. Normal and random and independent. So let's go with this. Example. Mrs. Smith's class wants to construct a confidence interval for the proportion P of pennies more than 10 years old in their collection. Their sample had 57 pennies more than, that should see then, not that, I'll fix it, than 10 years old, and 45 pennies that were more, at most 10 years old. Check that for conditions for constructing confidence interval for P are met. Okay, so we're going to check to see if the intervals are met. Random. The class took a simple random sample of 102 pennies from the collection. So it is random. All right, we check normal. Remember that that is N times P hat. So 102 times 57 over 102 is 57. And N times 1 minus P hat is 102 times 45 divided by 102, which is 45. Well, both the number of successes and the number of failures are greater than 10. So it is normal. Independent? Okay, well, since we're sampling without replacement, then the number of pennies in the population must be at least 10 times 102, which is 1,020. Since there are more than 2,000 pennies in Miss Smith's collection, the 10% condition is met. So check your understanding. So stop, pause this, and check your understanding on page 487. Wow, that's a jump. An AP statistics class at a large high school conducts a survey. They ask for the first 100 students to arrive at school one morning whether or not they slept at least 8 hours the night before. Only 17 students said yes. All right, well, let's check. Random? Nah, it's not random. This is a convenience sample. More than likely, the people that got up that early in the morning and arrived there first probably didn't get as much sleep as somebody that slept in. All right? Normal? Yeah, the normal's met. Our N times P hat is 17, and our N times 1 minus P hat is 83, and they're both at least 10. And the independent is met. This is a large high school, so there's probably more than 1,000 students there. All right, number 2. The quality control inspector takes a random sample of 25 bags of potato chips from 1,000 bags filled in an hour. Of the bags selected, 3 had too much salt. All right, let's check it. Random, met. Yeah, that's random. Normal, not met. Okay, because n times p hat equals 3, and that's not at least 10. Independence, met. Yeah, there's thousands of bags produced per hour, so the sample is less than 10% of the population. All righty, let's move on. All right, constructing a confidence interval for P. All right, you should be reading this. Standard deviation is the measure of variability of a statistic. When the standard deviation of a statistic is estimated from the data, the result is called the standard error of statistics. It is the standard deviation of the sampling distribution of the sampling mean. Yeah. We use standard error when working with confidence intervals or whenever we don't know the population standard deviation. So that's when we use standard error. Alrighty then. Moving on. Alright. What is the formula for the standard error of the sample population? How do we interpret this value? And is this formula on the formula sheet? Always want to know that, don't we? Alright. Recall that the formula for finding the standard deviation of the sampling distribution of p hat is, okay, it's the square root of our population proportion times 1 minus the population proportion over n. All right, well, since we don't know the value of p, we replace it with the sample proportion p hat. So the standard error is p hat times 1 minus p hat over n. Same thing, only we replace the p with p hat. All right, so let's move on. The standard error describes how close the sample proportion p hat will be on an average to the population proportion p in repeated simple random samples of size n. And the formula for standard deviation is on the formula sheet. You'll just have to know when to use p hat. And more than likely, that's all you'll have is p hat, and so you'll know to put it in there. Okay, what is a critical value? How is it calculated? And what does this asterisk mean? All right, well, a critical value Z star is the cutoff value for the computed test statistics that defines statistical significance of a test. It measures standard errors you need to be C% confident, or whatever percent confident. For a 95% confidence intervals, we estimate the critical value by using table A, or the calculator. So it's kind of like the Z-score, right? We're looking for the Z-score. We're given the confidence intervals, and so we are going to kind of do the reverse Z-score. Instead of finding the Z-score and then looking for the percent or the area under the curve, we've given the area under the curve, and we are going to be looking for this Z star. Alrighty? Does that make sense? Alright? So, how is it calculated? Well, like I said, we can use table A or the calculator to do this. And what does that asterisk mean? Well, we use the asterisk to remind us that this is the critical value, not a standardized score, Z, that has been calculated from the data. So it's just to remind us that it's not Z. Z star. All right. Okay, so find the critical value of for a 96% confidence interval for a proportion. So here's our normal curve. All right. Here's our mean. Remember that's 96. That means there's 4% that's not included in our area. So we're going, since that leaves us with 0.0 or 0.04, we divide that by 2 for the upper and lower areas. And so that's what we're using. We're going to find this area right here. Find the critical value. Let's go with that. All right. For 96% confidence level, we need to capture the middle 96% of the standard normal distribution. This leaves 2% in each tail. So we want to find the z-score for an area of 0.02 to its left. The closest that we can find, the closest entry for z, and this is using our table, is a negative 2.05. The critical value we want is z star equal 2.05. So this was found in table A. What is the formula for a one sample z interval? Once we find the critical value z star, a confidence interval for the population proportion P is the statistic, if you recall, the statistic plus or minus critical value times the standard deviation of the statistic. So what we're going to do is we'll have this formula for this one sample z interval for a proportion. So choose a simple random sample of size n from a population that contains an unknown proportion P of successes. And an approximate level C confidence interval for P is P hat plus or minus Z star square root of P hat minus times 1 minus P hat over N. Okay, where Z is the critical value for the normal, or for the standard normal curve with the area Z between negative Z star and positive Z star. Use this interval only when the number of successes and failures in a sample are both at least 10 and the population is at least 10 times as large as the sample. So this is our formula that we'll be using. That's after we find Z star. All right? So, let's see how this works. Okay. All right. Let's take a look at this example. Students in an AP statistics class want to estimate the proportion of pennies in circulation that are more than 10 years old. To do this, they gathered all the pennies they had in their pockets and purses. Overall, 57 of the 102 pennies they have are more than 10 years old. Identify the population and parameter of interest. Okay, well, our population is all the pennies in circulation. The parameter is the pennies in circulation that are over 10 years old, or the proportion of pennies in circulation that are over 10 years old. So check conditions for calculating the confidence interval. Remember what we have to check. First, random. And random is met. There is no reason to believe that the pennies were not given randomly to the students. Normal, that's met. Check it by multiplying 102 by the number of successes and 102 by the number of failures. And both of these numbers are greater than 10. So normal is met. And then last of all, independent. And that is also met. If we multiply, this is our 10% that we're looking at. So multiply 10 times 102 and we get 1,020, and I don't know if there's millions, it probably is, but there's a heck of a lot of pennies out there in circulation, so the sample is less than 10%. So all of our conditions are met. Construct a 99% confidence interval for the parameter. All right. Let's take a look at what that would look like if I drew it. Okay, so this is what our confidence, our normal distribution looks like. This is the 99%, and since there's 1% left, that would be 0.5% and 0.5% over here. So we're going to be looking at this tail right there. Just want you to make sure you understand where I'm getting the 0.005 when I work this problem out. Construct a construct a 99% confidence interval for the parameter. There we go. All right. So p hat is 57 over 102, which is 0.55. Our proportion is 0.559. The critical value for 99% confidence level can be found by looking for the point that has an area of 0.005. That's to the left. We're looking at that left tail. The calculator's inverse norm 0.005, comma 0, our low end, and 1, gives us a negative 2.576. So the appropriate critical value for 99% confidence level is Z star, it should be, equal 2.576. Now the 99% confidence level is, remember how we find that, p hat plus or minus Z star times the square root of p hat times 1 minus p hat divided by the n. So put those all in, and when we work this problem out, we end up with 559 plus or minus point, this right here, when we work it out, gives us 0.127. Now this is how we write that interval. It's the interval from 0.432, if we subtract 0.127, to 0.686, and that's if we add 0.127. So interpret this interval in context. We are 99% confident that the interval from 0.432 to 0.686 captures the actual proportion of pennies in the collection that are more than 10 years old. Is it possible that more than 60% of the pennies in circulation are more than 10 years old? Well, yeah, of course it is. We have between 43% and 69%, about 69%. So, yeah, yes. Since 0.6 is included in that confidence interval, it is plausible that 60% of all pennies in the collection are more than 10 years old.